So hello everyone. So we start a session of applications of ASP number 2. And we have 3 talks in this session. The first talk is given by Denise, Angelica.
Yes.
The title is Integrating ASP-based Incremental Reasoning in the Video Game Development Workflow.
Thank you for the introduction. Hi everyone, I'm Denise from the University of Calabria in Italy, and I'm presenting a joint work with Ianni, Francesco Pacenza, and Jessica Zangari about integrating ASP-based incremental reasoning in the video game development workflow. So nowadays, artificial intelligence is widely used in multiple fields, and one can think that the video games one is the least important, but it actually occupies a big chunk of the world economy. And moreover, you don't have to think about video games as the classical way of escaping the everyday routine, but also you can see video games as a way of reenacting everyday scenario. Like, for instance, you can have traffic congestion simulators, and also think about Formula One drivers that use simulators to improve their performance. So this is not a toy case. And AI is used in multiple ways in video games, and also, as Chris talked this morning about content generation, that it's a really important part of a video game, because if you want a game that is catching, you need to have realistic or fantastic worlds, depending on the genre of the game. And these often are very large worlds. So you need a clever way of generating these maps, let's say. But another way that AI is used, and it's important in a video games, is the way of programming non-player character, also known as NPC, because those are the characters that the human player will interact with, and you need those to be acting like if played by a human. So they need to be challenging, but not unbeatable, because it's not interesting to deal with a too tough enemies. No, you can't beat him, you are annoyed, so you won't play that game. And all these AI tasks in the video game design process are often boring and require a lot of manual effort. So the video game industry is always looking for new methodologies and techniques to achieve their goals. Machine learning is used, of course, but there are some limitations, like, for instance, think about the need of retraining a neural network every time you need to introduce a slight modification to a non-player character behavior. So there is room to introduce the declarative tools here, and among all the possibility, we choose to focus on the answer set programming. I won't go in detail here, we heard about it in previous sessions, so I will directly go to the why not part. Declarative logic has been used in video games in the past, but it was not capable of catching professional game designer interest, mainly because, as we know, there are drawbacks for declarative languages, like, for instance, it's not easy to integrate them in object-oriented environment, and they are not fast enough to cope with real-time scenario. So in the end, I will say also that they are not so declarative. I mean, if you take someone that's walking down the streets and give them an ASP encoding, or even worse, a prolog one, they won't understand what's in there. So we have a lot of disadvantages, but we have some good points to talk about, like They are useful to save a lot of development time, and also the community is working in the real-time speed direction. So with this talk, I want to show you two tools that our group work on, that are the ThinkEngine and Incremental DLV2. And with this actual work, we integrated the two of them. So I will go through the integration process. We will discuss some experiment we did, and most important, we will talk about some interesting lessons that we learned. So ThinkEngine is a tool that is actually an asset for the Unity game engine, that one of the most used in the game community. And we offer a way for wiring ASP-based brains to games developed in Unity. You can use it for defining NPC behavior or for content generation and so on. We currently support Klingo, DLV2, and now also Incremental DLV2. And we give the possibility to use two different brains. One are the reactive brains that allows to directly apply to the game logic decision derived from the reasoning process, while running brains are used to synthesize a list of action that you can see as plans, and these plans can be prioritized, overridden, or even aborted. So the architecture of the ThinkEngine recreates somehow the hybrid deliberative sense think act models, in which the think phase has been detached from the main loop, so that even if the solver is not so efficient, the graphical interface or the game logic won't be affected by this slow process, let's say. These run in external threads, and to access the solver, we use the MBASP framework that actually exposes some API to connect the object-oriented world and the actual solver. So due to some limitation of the engine, we had to introduce this data passing layer, mainly because external threads have not access to the game logic. So we needed to make the solver aware of what's going on in the game. Of course, introducing this layer introduced also a delay in the passing process, so we are currently working on optimizing this step. I will just show you briefly how the ThinkEngine works, and at the same time, in a Unity project, you can graphically choose which object to use as sensors, so that we become facts of your AI, and in a similar way, you can choose which object to act on. In this case, we choose the direction followed by the Pacman. And at this point, once you have done selecting sensors and actuators, you have just to focus on writing down your AI. It means you have to write your ASP encodings, and at real time, at runtime, the ThinkEngine will put all together in a completely transparent way for the developers. So moving to Incremental DLV2, it's an incremental reasoner. But before going to explain what this means, I want just to recall what the classical ASP computation is. And that's it. When we have an input program that has to be run over some facts, the first thing that is done is the grounding. It means to substitute constants present in the facts in the non-ground rules of the program, thus producing the actual propositional program over which the solving phase will be performed and answer set will be produced, if any can be produced. You can see this process as a whole one, as a single shot, that starts with input and ends as soon the answer sets are produced. The limitation here is that if you have to run the same program over multiple initial states, you will waste time because you could easily reuse something from the previous grounding steps, but since it's a finite process, you don't have access to those information. So we actually want to move from a single to a multi-shot reasoning in which the process doesn't end as soon as the answer sets are produced, but actually at that point, it waits for new inputs to come in, and the previous computed propositional program is used alongside this input to generate the new ground program. So the main approach behind this incremental reasoning are the overgrounding and overgrounding with tailoring. I will just show you both, mainly highlighting the difference between the two of them. So the basic idea behind overgrounding is that once you have a ground program, let's say at iteration 1, at iteration 2, you will just compute new rules based on facts that were not in F1. And so at a genetic iteration I, the ground program will contain all the ground rules computed up to I-1 with the addition of the new ones generated depending on the facts of iteration I. So the answer set at iteration I will be computed on a very huge ground program because it collects all that has been computed up to that point. Overgrounding with tailoring instead wants to boost the ground efficiency, taking under control the memory consumption, because if you continue to enlarge the ground program, the memory will become a problem. So once at iteration 1 you compute your ground program, you start to simplify rules according to the facts, like eliminating rules that have no chance to be triggered because you know for sure that the body is false, and also you remove pieces of rule of body that you know are true. So it's useless to bring them up to the solving phase. And at next iteration, you have maybe to revert this simplification because maybe a fact that was true at iteration I-1 is no longer valid. So the simplification you applied is not valid anymore. And once you have desimplified the ground program of iteration I-1, you can then compute new rules depending on Fi and simplify them again according to these facts. So you can see now the ground program as tailored on the input facts over the current shot, and thus computing the answer set will be faster with respect to the execution with the classic overgrounding. So we based incremental DLV2 on the overgrounding with tailoring approach, and thus we obtained a solver that remains alive till you kill it, basically. So you, in the first shot, give it the input, you give it the program as an input, and then you will keep feeding it with the facts from shot to shot. So here I want to point out that the ASP syntax is perfectly the same as the single shot one. So the program is not affected by this approach. It's all done in a transparently way for the user. So coming back to the integration in the ThinkEngine of the incremental DLV2, the main problem here was that this process remains alive till the end. And when we came up with the ThinkEngine idea, we didn't think about staying alive process. So we had to adapt the architecture, the infrastructure of the ThinkEngine to accommodate the incremental DLV2. But once we were done with it, we wanted to test the performance of the incremental reasoner, and we used 3 video games as benchmark, in which we compared incremental DLV2 and DLV2. And as a first example, I have the Frogger one, in which you have a frog that has to cross a road while avoiding some cars. Then it has to ford a river, exploiting some trunks and turtles floating over it. We have a reactive brain here that, as I said before, allows to directly apply decision to the game logic. And if you need, you can also verify a quick condition before applying this decision. For what concerns planning brains, I want to just add something to what I said before, because I said that plans are a list of action, and I want to point out that this action can have some prerequisites that must be written in the procedural part, so in C# in particular. And depending on the outcome of checking these prerequisites, the action can be skipped, executed, or make the whole plan abort. That's important because the game world is dynamic, is non-deterministic. So meanwhile you are computing your plan, till you're done, it could become useless because maybe something happens in the game, and what you did has no sense anymore. So the first example we use is the Space Invaders, in which we have 3 planning brains, and the goal of the game is that this green shuttle down here has to shoot these incoming invaders while trying to stay alive. So the first planner we had is an emergency one that just takes care of avoiding these incoming bullets. And then we have the other 2 brains that are triggered depending on how many invaders are left in the scene, and they have the same goals, to kill the invaders. Then we have the Pac-Man example. Even here we have 3 planning brains, an emergency one that in this case, it's responsible of make the Pac-Man run away from 2 close ghosts. Then we have a fast AI that look for the best path to follow, leaving the Pac-Man being distant from the ghost, and in the same time it has to collect the highest amount of Pac dots as possible. And in order to be fast, the distance between points of the map are computed with the taxi cab metric. Then we have the last brain that has the same goal as the fast AI, but in this case, we actually use distances between points, taking into consideration the configuration of the maze. So all these brains have their own features, and the most important I want you to focus on are these 2 brains that have a really high number of possible constants. And that's because the encoding, the ASP encoding, is to a pixel level. So we have a really fine-grained input. and I'll show you why this is important now. Let's compare the average time took from the incremental reasoner and the classical one. As you can see, in average, in each shot, the incremental reasoner is faster than the classical one. And this is not the truth for those two examples that I pointed out before. And if you take a look to the memory, you see that the incremental reasoner completely lose control over the memory usage. And that suggests us that this fine-grained information do not fit at all the incremental approach. So coming back to the time, I want you to look to these results in the emergency planner of the Pacman. And as you can see, the incremental reasoner is more than 2x faster than the DLV2. And in order to give you an idea of why this is an important result, take in consideration this scenario, and I want you to think about how long can take the Pacman to go from this point to this other one. This is an intersection, a good point in which you could change direction, maybe if you are chased by ghosts. And take a look to this timer, and you see it took less than 3/10. In these 3/10, you have to sense the word data, pass it to the reasoner, wait for the reasoner to compute your answer set, and once you have the decision, apply to the game logic. In less than 3/10, the LV2 took more than 3/10 just to compute the answer set. So even if it's a few amount of time that you are gaining going from DLV2 to the incremental DLV2, in a real-time scenario, this is a really important achievement. So just in conclusion, as I said before, we noticed that these two fine-grained information are not good for declarative logic in general. Thus, we want to introduce an abstraction layer in order to prevent this kind of situation. And we also want to give the developers the possibility to define declaratively other known NPC behavior specification methods, like, for instance, finite state machine. And we would like to make it easier to an object-oriented developer to approach a declarative formalism. And last but not least, we need to speed up the data sensing step, because these really affect the performance of the ThinkEngine. So if you want to take a look to our work, you can go to our GitHub, and you will also find a game showcase. Thank you for your attention.
Any questions? Okay. So could you show the slides of experimental results? The table?
Yes, I'm going to. I don't know. Okay.
Okay. So the time in the average, except two,
yes.
they are less than 1 minute, 1 second.
1
right?
second. Yeah. Yeah. Because in video games, you have really to be fast, because the world is changing very rapidly. So if you don't respond in this amount of time, you will produce answers that are not useful anymore. So the faster you are, the better are the results that you will achieve.
Okay, thank you. So, any question? Any other question?
That's great work. I wonder how do you obtain the programs? for the brains, let's say?
The encodings, you mean? We wrote them. We just want to show that in a few minutes of an ASP programming, you can obtain similar results to hours of machine learning training. So we don't want to give the best player for that game. We want just to show that our approach is viable. You can write down a human-alike AI, and you can do it in a few minutes, possibly.
Okay, okay. So I guess a related question would be, I think when I first heard you talk about a reactive agent, this could also be the result of a computation, right? That you give a specification how your reactions should look like, and you come up with something like a reactive plan. And I guess you could also do that with ASP. So push it offline, let's say.
Yeah, that's an interesting point of view. We need to look into it. Thank you.
Other questions?
Sorry if I missed this, but did you use an existing incremental ASP solver? Is that what Incr DLV2 is?
Yeah, incremental DLV2, yes, is an incremental reasoner. That's different, for instance, from the multi-shot Klingo. That's another way of approaching this. Here we have a fixed program that will remain the same throughout all the process. So that's a bit different from that point of view, let's say.
Okay. Other questions?
Thank you. Can you tell us a little bit about the choice of games and if there are any other games that you would like to look at in the future?
Yeah, actually, we are a bit limited from this point of view because we are not game developers. So we look on the web for projects that are already there, or sometimes we have our students to develop some games and we make them write the AI for them. And for now, we are sticking to 2D games because we know that moving through to the 3D ones, there will be other challenges to face. But we want to go in that direction, and maybe also having more than one AI working together or in a competitive way. So we want to explore a lot more this world. Yeah.
Okay. Other questions? Okay. The games you show remind me my happy time of childhood.
Yeah.
Thank you very much. Thank you for the
Thank
speaker.
you.